Yeah, my pleasure to be here. I thank the organizers for the invitation, and I'll tell you about Motivic invariants of birational maps. So basically, the whole thing will be about certain homomorphisms from birational self-maps of X, as defined in the previous lectures, to some other groups. And specifically, if X is n-dimensional variety over a field K, so typically we'll take Pn or something like this, we'll go to a certain group of smaller dimensional varieties. So we'll be looking into so-called Burnside ring of n-1 dimensional varieties over the field K. So what I'll do today, I'll define this homomorphism, and in particular this group on the right, and we'll do some easy examples of this map. So this C stands for centers. So we called it C as in it incorporates centers that we blow up and blow down when we look at this birational map. So Motivic is kind of a big thing. For us here, it will mean that it's universal in some sense and is built from algebraic cycles. So that's the vibe of being Motivic. So universal and coming from algebraic cycles. To motivate this kind of invariant, I'll introduce two questions that it helps solving in general. The first I call Gromov's cancellation question. And this question is not about birational maps, it's about birational types. So it asks the following. If you have two closed embeddings, you have two closed subvarieties in a big variety W, and assume that you know that the open complements are isomorphic. Yes, you managed to have such embeddings so that open complements are the same. The question was, does it mean that X and Y are birational? So Gromov was more careful. He wasn't asking exactly, he was saying like under which conditions on X and Y they are birational, but at that time there were no counterexamples to this. And we'll see how to make examples to this kind of questions. So the answer is not always, and the invariants I'm talking about are controlling this kind of cancellation questions. Cancellation in the sense that kind of, can you cancel out if you have the same variety and the same open, does it mean you can cancel them out and get something on the closed complements? That's question one. And question two is concerning what are Cremona groups generated by. Specifically, we can ask, are Cremona groups generated by elements of certain type? We can ask elements of finite order, or more generally, regularizable elements, as mentioned in Michel's talks, regularizable, or more generally, pseudo-regularizable, and so on. So I'll recall later what this means, but kind of we'd like to know how to maybe disprove that certain groups are generated by certain simple kinds of elements. And for both of these questions, we can use the invariants I'm talking about. So I need some setting. So to define the invariants, I'll recall the category work in. So we take any field, and again, as in Christian's talk, because this is so general as a definition, there's no assumptions on the base field. It's a formal construction. And we'll look at a category of birational types. So the category consists of objects and morphisms, and the objects here are varieties over K, and my varieties actually are irreducible, and morphisms are birational maps. birational maps. In other words, birational isomorphisms. So if x and y are not birational, then this is empty. But if x is equal to y or something birational to y, then there are birational maps between them. So they're not just rational, but birational. So we usually won't write this. Usually all my maps will be birational. And so it's a groupoid, a category where all morphisms are invertible. Yeah, so that's the category of birational types I'm working with. And so the target of this homomorphism is the set of isomorphism classes in this category. So following Kontsevich and Chinkel, we can look at Burnside group. Nth Burnside group is the set of, it's a free abelian group on n-dimensional birational isomorphism classes. Yeah, so I have a category, and I can look at the set of isomorphism classes of objects. And in particular, we can look at one dimension at a time. We can also look at the whole thing, which is the direct sum of all these guys over all dimensions. So this was a group. This is a Burnside ring of Kontsevich and Chinkel. They define this for some other purpose, but it's convenient for us to use this notation. And in a second, I'll connect to the classical Burnside ring of a group, if you know what this means. Yeah, so it's a very formal thing. It's a huge free abelian group on a certain birational types, and you can also put all of them together as a ring if you want. So indeed, right. So if I have two classes, x and y, we take the product. There's a little subtlety that that this is not always irreducible, and then you have to take the direct, the sum of all of them. So it's almost a monoid ring, but with a little subtlety that if there are components, you have to separate the components. If case algebraically closed, there's no such problem. So let's think about this gadget in small dimensions. Specifically, let's look at dimensions 0 and 1. N equals 0, we're talking about zero-dimensional varieties. So zero-dimensional variety is spec of a finite field extension. Sorry, irreducible. Zero-dimensional, yeah, okay. All of them are irreducible for me, so finite field extension. So I want to connect to this classical Burnside ring of the Galois group in this case. So let's assume K is perfect field. For this example, then to give such a thing is the same thing as to give a finite transitive G set. So if you think of your finite field extension, what happens to it over algebraic closure? It becomes a Galois orbit of points. And this is my G set I'm talking about. And that's a standard correspondence. Grothendieck's Galois theory corresponds between finite field extensions and finite G sets. And so what I'm saying is that the zero-dimensional part of this Burnside ring is just what's called Burnside ring of a group. So if you've seen in representation theory, Burnside ring of a group is free abelian group on G orbits, on finite G orbits. So here it's a bit more complicated. It's profinite group, but ignoring these profinite issues, that's the zero level of the Burnside ring. So it's much bigger than the Galois group. Yeah, and it's kind of important for us that we have zero-dimensional varieties, and one can study them if needed here. Another example, maybe a bit more familiar, is curves. And then this, so because every curve has a unique smooth projective model, maybe regular projective model, we can say that this one-dimensional Burnside group is the same thing as Z on regular projective curves over K. So there's no birationality relation, it's just isomorphism. So I'm looking at all regular projective curves up to isomorphism over my field. And then in dimension 2 and so on, it gets more and more complicated or interesting. So in a second, we'll have some invariants with values in these groups. But before that, let me just define what kind of invariants we consider. Yes. Yes. So that's it's just the same thing, but now on finite. So it's Z on finite transitive G sets. Right, so you look at G orbits, and you make, for each possible G orbit, you make a generator, and this way, if you have a finite G set which is not transitive, you assign some multiplicities in here. So just its zero-dimensional varieties correspond to Galois sets, and this is a particular case. Yeah, this wasn't a very important remark, but the point was that if you have seen Burnside ring of a group, this would be relevant. If you haven't, that's fine, that's the definition. I want to introduce now this additive invariance that we'll be talking about. So later on, we'll concentrate on self-maps. But to develop the theory, it's convenient to look at maps from X to Y and Y to Z and compose them. So I'll have target is an abelian group. And X and Y are varieties over K. And so additive invariant is an assignment like this, that for birational maps between all varieties, it assigns you values in abelian group. And being additive means it's additive under composition. So they're such that if you have X to Y to Z, then you have composable birational maps, phi and psi. Then you want this additivity property to hold. Yeah, so additive invariant just means it's for every birational map, you assign like an element in some target group such that as soon as you can compose, it's additive. In particular, for self-maps, you get homomorphisms. In particular, get group homomorphism from B or X to A. And this, if you want, is a groupoid homomorphism. So I had a groupoid here, and here is a group, and this is what we can call a groupoid homomorphism. Just when there's more than one object, we allow doing this. Yeah? It will follow, it will hold in for our invariant, but in general, I don't assume this here, yes. Indeed, for the invariants we'll consider, regular isomorphisms will go to 0, but here it's not part of the definition. Yeah, you can deduce some of this from the group law, indeed, like some of these properties. Okay, so I'll construct some of these invariants now, and kind of first, before introducing the one we'll work with the values in this Burnside group, I do something a bit more universal. So slightly more general version than the one we'll be using. Specifically, I look at some kind of group which is made up to satisfy these relations. So I look at certain other gadgets, K0 of pairs over K. So this definition makes checking certain things very natural and transparent. So this is a abelian group with generators and relations. So my pair is an open embedding. Up to isomorphism. So I'm looking at open subvarieties, or more like these maps, considered up to isomorphisms on the source and on the target. And they impose relations coming from compositions. So if I have V inside U inside X, I declare this to be equal to V inside U plus U inside X. All this is all these are huge abelian groups, and the point is whether we can make them useful for anything. And we can make them useful to make certain constructions natural. So right, so basically I'm kind of like what it does is sort of looks at the particular case of open embeddings and imposes pairs like this modulo these relations. Mm-hmm. Yeah. So basically, I'm allowing twisting them like this. So isomorphism of pair means I have another embedding and a commutative diagram with isomorphisms between these guys. Yeah, and the kind of dilemma, which this should look a bit like universal target for this homomorphism. So the dilemma is that we have a additive invariant, we have a unique, we'll see examples a bit later today. So I'm going from birational maps from X to Y, and this K0 is this general kind of thing. So as soon as you want to impose some kind of cut and paste relation like this, you call it K0 of some category. So it should be considered just as one sort of symbol. Right, such that for every open embedding, I'm sending the open embedding onto the corresponding generator in the target. So, okay, once again, so I want to construct additive invariants with some values, and currently I'm doing something more universal than I will later use, but something which makes the proof very natural. Namely, I just define the symbols like this, and I map everything onto these symbols. And I'm saying that, so there's a couple of things which I said here, that first of all, uniqueness will be that it's sufficient to define everything on open embedding, an existence one has to make a little check. Yes, thank you. So, right. Okay, good. So this x and y are vary. So birational additive invariant takes any kind of x and y as an input. And so I only fix them on, so maybe it wasn't the best notation. What I mean is my u is x and my x is y. So this was one of the, I'm fixing everything on open embedding here. And everything else will take care of itself. Yeah, thank you. So sort of, maybe, I don't know whether you like it or not, but maybe I just remove the argument, so it's some kind of functor here. Okay, so this is such a formal statement that there's not much to prove. The thing is that it's some kind of strong factorization of birational maps into open embeddings. So the key point is birational maps admit factorizations into open embeddings. So if I have x and y, I can go with an open embedding here and an open embedding here, and then the composition of this birational maps is phi. So I'm saying I can do ji inverse. So for every, it follows from the definition that Michelle gave this morning that birational map will have the same open subset in the source and the target, and formally the inverse of birational map is a birational map. Therefore, I have this decomposition which I can play with. So it's like blow-ups, but much kind of easier than blow-ups. We just remove things we don't want to have. So for example, like what it means, how do I define, how do I extend that definition that I was giving to this phi? So I'm saying this is, by the additivity property, the only thing I can do is to take this minus this. So I'm forced to do that by the additivity, and this is my definition, actually. So to make sure it's well defined, we have to compare two of these factorizations. So let's say, so what we have to do is we have to make another choice and see what happens. So I chose one factorization of birational map into open embeddings, and maybe someone else chose another one. So I'm looking at this diagram. And this strong factorization property says that I can just intersect them. So I can take u double prime, embed this here and here. And so basically what I have to check is that my output doesn't depend on the open set I look at. So this intersection process allows to consider just subset, replace u by a subset. And then you look at maps in this diagram, and you see that, for example, if you replace u by u double prime, you have to go this way versus kind of this way. But you end up seeing the same thing, plus and minus the same term, and there will be some cancellation going on. Yeah. So first of all, we're used to looking at subset in U, and second, you notice that this is independent. What I'm claiming is does not depend on the choice of U. So that's well-defined as you look at this diagram and you see that the outputs are the same. This is like strong factorization, like something we don't have for blow-ups, but we have by definition for open embeddings. We could take some kind of maximal one. However, when we start composing, like I do in a second, it's best to allow arbitrary U here. Yes, good point. Maybe there's a canonical U, indeed the maximal one where phi is defined, but it's, yeah, let's see what we do for compositions, which is the last thing to check in this proof. Basically, you have to find a U, first of all, which maps here, here, but also here. And it's best if it's the same U which does it, because then you can just use it for, there's like I, J, and K. And by this property, you just take U that you want, maps everywhere here, and then you take, you know, for the first map, yeah, I'm saying how it's additive. You take like this minus this. For the second, you take this minus this. Altogether, this minus this. Yeah, so yeah, so this is uniqueness, existence, and the property we were controlling. Yeah, so this has some kind of universal flavor. So in fact, one can show that every additive invariant will factor through this group. So hence, to construct additive invariants, we can like forget some information from this K0 of pairs and work with some smaller data. And specifically, so here is the composition we look at. So we define the main Motivic invariant, so Motivic invariant C that we work with. You go from X to Y into this K0 of pairs, and then I want to forget something. I want to forget information I don't care about at the moment. I'll go to Burnside of n-1 dimensional varieties, where these guys have dimension n. And so I need to tell you where I send a generator here. This is an open embedding. And kind of I need to tell you how I make n-1 dimensional subset, but it's clear how I make it. I take a complement, right? So I write, I look at x minus u, that's closed embedding inside x. And I look at divisorial components. Divisorial components of this set. And I map this to the sum of the divisorial components. So I have a lot more information here. I have this kind of open embedding and like maybe some points in the complement and stuff, and also some kind of birational geometry of this whole pair. There's more stuff here. But instead, I just say, take the divisorial component of the complement and look at their birational types. So look at birational types of those components. So what I'm saying here is that this is a homomorphism. This group was given by generators and relations. Is there a question? Mm-hmm. Yep. Mm-hmm. Yeah, thanks. So I guess, yeah, thank you. So this will be n-dimensional pairs, and these are n-dimensional varieties. Yes, so indeed, it's done at one level at a time, and also all together at every level if we want. Thank you. So one thing to check is that relations in the source are preserved. So basically, you have to think of, so we need to check. What I'm saying, okay, what I'm saying is that I want to take this composition C, which first does the complement and then does the divisorial components of that complement. And what I need to check is that if I have V inside U inside X, divisorial components as here respect this composition. And they do respect this composition. So if you think which divisors are missing here, here, or altogether there, just a union of this. Yep, so divisorial components add up under compositions. Right, so this will be the main invariant for my four lectures. So the input is a birational map between n-dimensional varieties. I find an open set in both of them, which is common, and I look at the other guys, the divisorial components, the complement, and then I record them with signs. So explicitly, what I'll have to I'll just want to spell out explicitly what we're computing here. So if I have a birational map from X to Y, if you look at D1, Dm, and E1, El, so these are divisors in X, these are divisors in Y. I'm looking at some kind of exceptional divisors such that I can compare X minus the union with Y minus the union. So I would like to write like isomorphism here, but this is isomorphism in codimension 2. So what's called a pseudo-isomorphism, i.e. it has no exceptional divisors. It's well-defined, an isomorphism in all divisors. No exceptional divisors. So this is kind of what it means to take divisorial component. You mark all the divisors where you have a problem with, remove it from both sides, and then you set that you're counting the new divisors on the target that you have created minus the divisors on the source, which you don't have anymore. As you may guess, this thing, we don't have to look at divisors. This could be made a lot more precise, like look at codimension 2 and so on. But for all the applications I have, divisors are sufficient. And that's kind of the natural language to consider these things with. Yeah, so I'm introducing new divisors here, and I'm removing these divisors, and this is my invariant. Because I could factor this as a composition. I could compare this with X, Y, like this. And this is kind of like an open set I had before, modulo some codimension 2 stuff, which I ignore everywhere. So the key example to keep in mind is the blow-up. So this formalism is developed like naturally, originates from open embeddings. But what we really want to know is birational maps between smooth projective varieties. So blow-up is the key thing we want to control. So if x tilde to x is a blow-up of a smooth Z, then there's one divisor missing in the target. So contracting this divisor sort of is the same as removing it from this perspective. So I have to put a minus sign and then the exceptional divisor. So the exceptional divisor is a projective bundle over the center that I blow up. I just have to put the correct projective bundle to match the total dimension, and the correct bundle is codimension -1. So C is codimension of Z in X. So that's divisorial replacement for Z, and in this direction it's recorded with a minus sign because X tilde got smaller. And also because in principle that's a projective bundle, but because I consider my classes here in the Burnside group, so up to birationality, I can just say it's okay. I don't care which bundle it is, just make a trivial bundle. But in principle, this space is a projective bundle over the Z. But for us, it's just this. If you have an elliptic cone, you blow it up, you get something different, right? So if you have like a badly singular Z, then the exceptional won't have this form. So you need some kind of generic smoothness here for this to make sense. Yes, for example, if you have like cone over something, you blow up the cone point, and the divisor does not look like this at all. It looks like what you have cone over. Yes, and also like part of this formalism is that the inverses, because homomorphism from a groupoid, the inverse comes with a plus sign here, right? So I can do phi will be minus, phi inverse will be a plus. So I'll give some simple examples now for how to compute this. Yes, the first example is, of course, the Cremona map. Cremona involution. So as we know, we can resolve this map by blow up and blow down, where this thing is the Del Pezzo surface of degree 6. So you blow up 3 points here where your map was not defined, and you do the same thing on the other side. And then you can compute that for this map sigma. Basically, it will be like 3 minus 3. So what I'm saying is that you first created 3 new P1s, and then you got rid of your 3 old P1s. 0. That's one thing we can say. Another thing is, because it's involution, actually, so it squares to 0, so it squares to 1, but the target of the invariant is torsion-free. Therefore, every involution will actually have invariant 0 just because there's no torsion in the target. Another reason is sigma squared is identity, hence 2 times is 0, and this means that it's already 0 because we are in a free abelian group. But just to recall this picture a little bit, so kind of things like this can be generalized further and further to various non-closed fields, and it's sometimes important to consider this over non-closed fields. Over non-closed fields, instead of saying, let's blow up 3 points, you say, let's blow up a Galois orbit of 3 points. And then you have another Galois orbit of 3 points contracted here. In that case, instead of this 3, you have this little zero-dimensional scheme corresponding to the Galois orbit you blow up. And the same thing on the other side. But interestingly, these 2 Galois orbits are isomorphic, because there's a Galois invariant bijection between lines and points in this picture. Therefore, even over non-closed field with slightly different computation, it's still a 0. That's my first example. Next example is higher dimensional or arbitrary dimensional. Yep. Yes, that's right. If you, because this because our target group is abelian. It means that if you conjugate to something that you like, you can just replace it by that conjugate. If you conjugate an automorphism, it means you're zero, right? So that's another way. Yes, yes, even on a like a fine set, you're an automorphism, then you're still zero because you're conjugate formally in this category to an automorphism. By these properties, what we can see here that if open embedding is an isomorphism, then actually the answer is zero. So this really tries to capture non-isomorphisms among all the birational maps. Indeed. So over algebraically closed field, we literally just carry the Picard rank and look at the difference. Over non-closed fields, it's more interesting Galois orbits that we blow up. And then it's more interesting theorem, which I'll state later today. Yeah, next example is you look at n-dimensional quadric. A smooth quadric. And we assume that it has a rational point. So I'm looking at any field, so it's interesting. It has a rational point, and I project from that point. So I go from Q to Pn. This is projection from the point x. Projection from a point x is resolved by blowing up that point. Let's blow up of the point x. And here I blow up something more interesting. So if you, for example, in dimension 2, I'm blowing up 2 points on the line. And these 2 points on the line actually are small quadric. So who is this z? So z is inside Pn minus 1. It's an n minus 2 dimensional smooth quadric. Yeah, I'm just explaining what gets contracted when we blow up this point. The cone of lines through that point gets contracted, and the base of that cone of line is a certain quadric of smaller dimension. And the familiar case is n equals 2, then this is 1 point, and that's 2 points. Yeah, so, and then what I'm saying is that for this map, I have to look at, so that's a codimension 2 blow up, so I just have to normalize it by putting a P1 times the center we blow up. And this is what we have created. Sorry, this is what we have contracted. And what we have created is just Pn, so Pn minus 1. This is the exceptional divisor over the point. Yeah, it's over closed field, it's not a big deal because this is also rational, but over non-closed field, there's some kind of other interesting quadric attached to your quadric, and there's something going on here. For example, even for surface of a non-closed field, there's a little zero-dimensional subscheme which controls your quadric by this map. So kind of what happens is that it's sort of easier to prove that certain values are zero than they are non-zero. So specifically, okay, let me give you the table which shows when this invariant vanishes and when it not vanishes. And that's the main question for this lecture, so we will explain when C of bir of x of certain x, so it's interesting to apply it to self-maps in practice, is 0 or not 0. And non-zero is surprising and interesting because, right, so if you remember, I had these 2 questions at the beginning. So if so, we have consequences, namely, so Gromov's constellation has negative solution. if you remember, Grove constellation question was exactly about this kind of situation, where I was asking, once we have identified the open subsets in the variety which was the same. So I had variety which was the same, and open subsets were the same. We want to know what about these closed subvarieties. And in the example when it not vanishes, it will precisely be these divisors being not birational to each other. That's literally measuring that kind of thing. That's one. And second is we won't be generated by a lot of reasonable classes of elements, so not generated by, okay, one can just say by elements on which this invariant vanishes, right? And these are finite order elements, regularizable, because if you are conjugate to an automorphism, then the invariant vanishes on that automorphism, but because it preserves conjugacy classes, it will be just 0 by trivial reasons. And more generally, pseudo-regularizable. Pseudo-regularizable means conjugate to a pseudo-automorphism, conjugate to a birational self-map, which doesn't have exceptional divisors either way. Yeah, so that's the more general. We have implications. Finite, as Michelle was telling us, finite order implies regularizable. Regularizable formally implies pseudo-regularizable. That's the natural kind of thing we're not generated by. And this, people were asking questions like this for some time. So I want to state the table and then, yeah, comment on this table when we have vanishing and non-vanishing. So I have n and k, right? So for field, I consider two cases. Complex numbers, which probably is what we are mostly interested in, and some kind of small fields. So small fields will be number field or function field. And maybe tomorrow I'll explain better what do I mean by function field, but some kind of very non-algebraically closed field here. And this is my n, so dimension of my x. 1, 2, 3, 4, and larger. Okay, so if I look at curves, smooth projective models have no birational self-map apart from automorphisms. Therefore, there's nothing to check here. Like if you replace your curve by a smooth regular projective model, there'll be only automorphisms. And so for every field, there's nothing to do. In dimension 2, we're looking at surfaces, and this is easy. This is the Picard rank consideration, indeed. So this is saying that if we have two surfaces and some birational map, and we look at exceptional divisors, you know how many you have blown up just by considering Picard rank before and after. In particular, if you go to from x to x, your Picard rank has to go back to where it started. So everything cancels, like in that example. Right, so this is interesting. This is, maybe I'll say some words about later. This is, this is like for every field, basically. So for any perfect field, this is 0, and this is theorem Lin, myself, and Zimmerman. So we have to use MMP and Sarkisov links to work this out. And it's not just a formal statement, it's really a property of, deep property of surfaces. Okay, dimension 3. Over complex numbers, it's 0, and I'll be explaining this tomorrow. And now for small fields, interesting, this is not 0. Specifically for all fields here, it's not 0. For P3. And I'll also explain this tomorrow. So tomorrow we'll have some kind of threefold session where we look at intermediate Jacobians here and some interesting construction here. And then from here on, it just becomes non-zero. So this is non-zero, and this is non-zero. And I'll speak about some of this in lecture 4. Yes, for Pn both, yes. So kind of vanishing means for all, non-vanishing means for some, and when we prove non-vanishing, Pn is the easiest thing to check because it has the most number of birational maps. Yes, will be Pn. I have a little bit more time. Maybe I'll say some words about, so basically, in this map, I said this is trivial, this is easy. Maybe I'll say some words about this theorem. Okay, so theorem by Lin, myself, and Zimmerman from 2022 maybe is that if S over K is a surface and K is a perfect field, then C of bir S is 0. Okay, so as I say, it uses MMP and Sarkisov links and goes in the following way. So you first of all can assume that your surface is minimal and smooth. That's minimal, smooth projective surface. There are 4 disjoint types of minimal surfaces. So KNF, so you kind of run the MMP on your surface, right? You can get KNF, that's one type. Another is ruled over a curve where the curve is positive genus. That's kind of a special type because it's still like their dimension minus infinity, but not rationally connected. Okay, and then there are rationally connected ones, which form 2 types. The first is Del Pezzo or conic bundle of degree at most 4, and Del Pezzo or conic bundle of degree, at least 4, at most 5. Small degree, large degree. What I'm saying is that, okay, first of all, what I'm saying is that the output of MMP is one of the surfaces, like Del Pezzo of rank 1, or conic bundle over conic of rank 2, or conic bundle over curve, or KNF. That's the first thing. Okay, I artificially divided them. I'll tell in a second why I have divided them like this. But the next claim, I'm saying that they're disjoint. They don't talk to each other. There's no birational maps between surfaces of these types. So the question is localized, that I have like different groupoids hanging around, and I have to get rid of each of them at a time. So no birational maps, like there's obvious, sometimes here it's already Sarkisov links are coming in. If you know Iskovsky's list, then you know that these guys only go back to these guys, and hence these guys only go back to these guys. Okay, so then here there's basically will be no birational maps, isomorphisms, your birational maps. So if it's KNF, right, it should be pseudo isomorphism, and in dimension 2, they are isomorphisms. Yeah? So isomorphisms. These are easy because the links are easy Sarkisov links over the base, because the base is preserved. The base is higher genus, therefore everything happens over that base, and you need to do links and you just see that what you have blown up, you have to blow down. Yeah. Okay, these are just a couple of links. There's not much to check. So again, easy links. And Yeah, and this is the actual difficult case. You have to do something here because it's a huge number of links, and what one does is one kind of just solves this problem kind of by hand. So one assigns to any surface of this type some kind of class, which only depends on the surface, so that if you go from one to another, so you can make a construction like this, such that if you go from one to the other, then what you will capture in the exceptionals are their intrinsic invariants times P1. Okay, so where does it live? This lives in Burn 0. I'm saying that I'm attaching to every surface it's some kind of atomic content. Atomic content of the surface in such a way that if you connect them by a process like this, the answer will be difference of their atomic contents. And in particular for self-maps, there will be nothing to do here. But to prove this thing for self-maps, you have to do this because links don't go back to the same surface. You have to really assign something for every class and then check all the links between them, but then you're done. And this is, has to do with neurons, Galo action on the neuron severity group on the surface, which is permutation type. And then you assign some kind of sets there and check that all the links work. Yeah, I have 2 more minutes. Maybe I'll give an example of what I mean in this kind of construction. Because it will connect to examples I gave earlier today. So I'll tell you what is M on P2 and on a quadric. And then I'll show you the 2 links, namely P2 to P2, the Cremona, and a quadric to P2. Yeah, okay, basically, okay, long story short, I assigned 3 here, right? So what is 3? So 3 points, 3 Ks in this kind of ring, so 3 disjoint points. This corresponds to homology of P2 being 3-dimensional with trivial Galo action. So I'm trying to extract some kind of Galo set which knows about my neuron severity cohomology. And for P2, it turns out there's nothing to do. What do we do for a quadric? So we have to, it will be some kind of length 4 scheme. So it will be 2 plus rulings of U. So what's rulings? So there's no rulings if it's over K, but over K bar, there is 2 rulings which are maybe swapped by the Galo group. And this is a Galo set of 2 rulings permuted by the Galo group, and that's my element. And again, homology of this quadric, there are 2 trivial pieces, and the neuron severity is this. Neuron severity, so middle homology. Right, and then we have to define all this so that it kind of looks good, and then we check all the links. So here it will be 3, but nothing happens here because it's adding nothing, so 0. And here it's that thing which I was talking about earlier. So you have this blowing up a point. Sorry, here you're blowing up a point, and here you're blowing up some 0-dimensional subscheme. And so what I'm telling you is that 0-dimensional subscheme here is the scheme of rulings on the K bar. That's one of those things one has to be checking, that intrinsically this Z for this Q is the set of rulings. And this is how all those links will work eventually. So, okay, maybe I'll just tell you what I'll do in the next lecture. So lecture 2, we'll do threefolds, as I said. So we'll be vanishing and non-vanishing for threefolds. Lecture 3, I'll introduce vertical and horizontal invariants. When we have fibration over the base, we can split the invariants into the vertical and horizontal parts. And finally, in lecture 4, I'll explain some new non-vanishing result using this vertical and horizontal invariants. And that's it. Thank you.
Okay, so I think I have two questions. So in that last example, you said the zero-dimensional subscheme corresponding to the set of rulings. Can you say more about its infinitesimal structure?
Not really. So over a perfect field, it's really like a Galois set. And when it's non-perfect field, there was a project how to like define the. Basically, okay, maybe your question, I think, relates to the fact, what if the field is not perfect? What do I do then? And there's no such theorem, indeed. Sarkisov links now work. We know that they work by a recent result. But this kind of thing is more subtle. In particular, it's not clear how to do this Galois theory in the non-perfect. So I don't know. If you mean like maybe your quadric is like regular but not smooth, yeah, I don't know.
Yeah, and the second question, so in that table you had this new C invariant which might not vanish in higher dimension. Is that leading towards a classification of higher dimensional varieties, maybe even not only in terms of their non-vanishing, but also the values that C takes?
I will, in the last lecture, I'll say something about the values, and basically, so there are kind of two principles, right? So the bigger the dimension, the more birational maps we should have, and right, like first for Cremona, for example, if you go from n to n plus 1, we're supposed to see this, and indeed this we see in the image of the invariant. We can blow up more stuff in higher dimensions. That's one direction. And the other direction is from P3 or Pn to less ruled varieties, right? Somehow the feeling is that Pn has the most amount of birational maps and other varieties have less, and this is a bit harder to control kind of for us. So, for example, for non-vanishing, typically they are for Pn or something highly ruled, and when they're like, for example, when they're maybe an F, there's nothing, but cases in between are hard, which are like kind of less ruled than Pn, and more ruled than KNF, a gray area of some kind.
Okay, good, thank you.
So do you also prove that the C of beer of Pn is the minimum possible value?
So,
that you obtain?
But this table says something like this, right? So value of n, or value of what?
So for P4, C of beer of P4 is different from 0. But is that the minimum value?
For n, or minimum value for what?
Like, can you find another four-dimensional variety for which C of beer of X is smaller than C of beer of P4?
It should be smaller. Right? So I think Pn would be the maximum,
okay.
because it has the most number of birational maps.
Okay.
And for example, KNF is the opposite, but values like ruled over some base is kind of harder to understand. And so I think if you take like elliptic curve times Pn, maybe it's provably less than Pn plus 1. So some things like this are easy, but some others are less clear. Sarkisov, I've never met Sarkisov. I think it was a student of Iskovskih, right? But I don't know what happened to him. So you've met him, Sarkisov. Okay. Mm-hmm. I'll ask you later.